So today I want to drive you through two tools that we need to prove the continuity of conditional entropy, uh, which is first the variational form lemma, and the second one will be H is not too concave. So that's our two lemma we want to prove. But first, let's concentrate on the variational form, which says that for any row AB belonging into the set of density matrices of AB, we have, so it's a quantum state, the entropy of A knowing B, which is equal to minus of the cultivations of row AB, density of X or row AB, minus infinity of TB, belonging to TB of T of row AB, meaning that AI is our TB. So it basically say that row AB is like the better state, like to identify what we have and we cannot do better. To sum up it, we can say like our conditional entropy is just the minimal distance between our real system with rho B and an imaginary system AI, where Alice will be totally decorrelated from Bob. This decorrelated world is represented by AI or TB, AI like the identity, like it just allows being to tell a maximally uncertain state, like pure noise, and TB just theoretical state that we imagine for Bob. Well, here it's like the real state with the stuff decorrelated, and so yeah, like the conditional entropy is just a minimal distance between our real system here and our imaginary system here, where all this is like totally decorrelated from Bob in both cases. Like it means like if we give Bob a false state like TB, like we just add artificial noise to our calculation, and so searching the minimum is searching the best approximation of our system. Our lemma just guarantees that the best approximation for it is simply the real system of Bob, which is Robbie. And that's a really cool lemma because sometimes calculate directly the conditional entropy is really hard to do, but thanks to this lemma, we transform an entropy problem into a geometrical optimization problem, which is the research of a minimal distance. That's this tool that will allow us after to prove theorems such as the capacity of quantum canals or the continuity of systems under the effect of noise, such as the entropy, the continuity of the entropy. So let us prove this theorem. So basically we have this at the beginning, like we will decompose it into two parts, First we will prove this equality, and in the second time we'll prove the second equality. And just to be clear, like, yeah, that's, the entropy stuff, and I said we go to distance stuff because, like, this is just the Cal divergence, which represent which ones two states are different from each other, what is, like, the distance between them in a way, are separated, like, so yeah, if, like, if this distance, like, if we have, for example, this equal to 0, then it just says that their states rho C are identical. um more zero, more our distance is bigger, more the states are far away from one of each other, and so more they are easy to distinguish from each other. Um, so yeah, it's just in a way like measures the quantity of information of our surprise that we lost by using the raw model, like TB instead of rho B in this case. So yeah, let's prove this theorem. And so that's cool, as I said, because we go from interface of just distance, so from to a geometrical optimization problem instead of entropy one. So let's go. We just prove first this. Um, so yeah, we want to prove this. So if we write like minus d of 3 rho ab, the first one, and ai rho b for the second stuff, then we can write it just minus, can put into bracket to not being wrong about the sign, and so it's just the trace of row AB log of um, row B normally, log of row AB, it's a log of 2 of course, and so it just minus trace of this, minus, so it's because it's like it's a formula, I just from like however I see it, just like trace of row, trace of row log row minus trace of row log C. Okay. Minus trace of row AB log AI for row B. Okay, so that's it. And so if we want to identify our first term, so this one, so instead of this, so we have trace of row AB. Well, maybe I can write it directly, as this, so it just means it's just equal to minus the trace of row AB, log of row AB, plus the trace of row AB of log of AR row AB. So minus of the trace of row AB log row AB, It's just the entropy of AB, because like it's minus J for log, so it's directly it's plus our second term, which is the trace of rho AB log of AI rho B. And so if you want to calculate our second terms into it, such as trace of rho AB, in a way of log of 2 of AI xer rho B, like I do not write like 2, like it's like 2. Then just like we can like first like try to just equal to the trace of rho AB multiplied by log of AI xer IB to having the same dimension as the matrices xer AI plus sorry AI xer LB. Like if we distribute just log of rho B, and so it's just equal to the trace of rho AB of the log of AI 0, because it's log of 2, but the identity is 1 on the step, so it's 0 multiplied by this, so I just conserved AI xer log 2 of rho B. And so normally like here at like trace of AB, it's on the same AB, but here like because AI is not here anymore, we can just apply the property saying that trace of rho AB AI or B is like just a trace of the stuff without I, like because the only stuff we have on I is identity. Um, and so we can just ignore it and just write the trace of rho AB, the trace of rho B, of log of rho B, which is equal to minus let me check about it. So minus h of rho B. And so if we assemblage this together, so h of rho B minus h of B, and just so the definition literally of h of AB, which is like A minus B, like it's h of rho AB minus h of B. And so we just prove the first equality, like because we have this equal to this. And so to prove the second one, minus d rho AB divided of minus d scalar difference between rho AB and AX rho AB is equal to minus infinity of the divergence of rho AB and AX or TB. So yeah, we just prove the first part, and so there's a second part, we just need to prove this one. And so to prove it, we are just gonna put this on the other side, and so I'm trying to see if it is equal to 0, for example. So we have g of rho AB of AI to rho B minus d of rho B of AI to rho of TB, and after we take infinity if needed. So we just calculate as earlier. So basically what you can say is that we will have a cancellation because we know we have a d of rho B here and minus d of rho B here. So basically d of rho B minus d of rho AB log etc. would be the same. Like I can write it still for educational purpose. So we have like d of rho AB sorry, trace of rho AB. You know you have trace of rho AB of rho AB minus the trace of rho AB of log of rho AB. So that's what I say at the console, you know, those two ones. So after you have the second terms, which are minus the trace of rho AB of log of AI to rho B mm, later to maybe do it in the other sense, like two can work, but like you know at the end our goal was just to have like this plus something being inferior being equal to like rho B plus something equal to TB. So well anyway, both should be working. So we have this and we have minus trace of rho AB and rho B plus trace of rho AB log of AI for TB. And so basically we just have same principle as earlier because we have this A, it doesn't depend of the system, so we can just isolate it. So we have minus the trace of rho B of log of rho B plus the trace of rho b log of tb. By the way, if you want the exact formula, it's this one. Like when you have like trace partial for no matter OB acting on B, and you have this A, like the property, like to say we have no matter is here, like because we do not have a dependence about A, um, we can write like just OB, OB. It's the main formula, you know. Oh, and the trace plus trace of Robbie of log of T. And yeah, it's just basically saying we have so the T of TB knowing Robbie. And so it just means that we have I just have like the D of row AB of AI XOR row B, which is equal to T of row AB of AI XOR TB plus DTB row B. So its real value is like attained when this is equal to 0. So when TB equal row B. So yeah. And so that concludes like we have inf of two AB of AX or TB is equal to 0 AB of X0 of rho B. And so we finished the proof because we found the solution for the second equality. Oh, sorry, I was wrong. I mistaken myself because I have trace of rho B here, trace of rho B here. So our first variable is like rho B. And so after here is TB. But like it just means because we have the inverse sign, we have minus, and so it just means we have like plus, so minus g rho b tb, But so we can pass this to the other side, and so we just give a plus, and so we just basically have this being the error, and so we have the inf, and so the better state we can have is row AB. And yeah, that's it.